Welcome back to Calculus 2. I'm Dr. Jeff Groh. Today, we're going to talk about two things. First, integrals involving trig functions, we'll call those trig integrals, and trigonometric substitutions, two separate topics. So first, trig integrals, and second, trig substitutions. To get an idea about trig integrals, let's look at the integral of cosine to the fifth dx. You'll remember the Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. That means cosine squared x is 1 minus sine squared x. But you have to convert them pairs at a time. Let's write this as the integral of 1 minus sine squared x squared times cosine x dx. We'll take one of these cosines and split it off by itself. The cosine to the power fourth is a cosine squared squared, and that's why we have 1 minus sine squared squared. It is at this point that you do a u substitution. U is sine x, because you have the derivative of something lying around. You can see that this will happen every time that the exponent is odd. You split one off and convert an even number into the other trig function. Du is then cosine x dx. The integral is transformed into 1 minus u squared squared du. Now we just FOIL this out and integrate this as a polynomial. FOILing out the square of the binomial, we'll have 1 minus 2u squared plus u to the fourth du. That's u minus 2/3 u cubed plus 1/5 u to the fifth plus a constant of integration. We're almost done. All we have to do is substitute back to get sine x minus 2/3 sine cubed x plus 1/5 sine to the fifth x plus a constant of integration. And now we're done. The procedure that we used in the last example works, but only if the exponent is odd. What happens if the exponent is even? Let's look at this example. Let's look at sine to the fourth x dx. If this exponent were odd, like 5, we would convert an even number of them to 1 minus cosine squared x's and leave the one left over as accounting for the du. Here, there's nothing to account for the du. So what do? Half-angle identities, always for these even powers. So let's review these half-angle identities. One of them is cosine squared x is 1/2 times 1 plus cosine 2x. And then there's sine squared x is 1/2 times 1 minus cosine of 2x. We're going to be using the second one here. We'll have the integral of the sine to the fourth is sine squared squared. So it's going to be 1/2 1 minus the cosine of 2x quantity squared. We'll get a 1/4 out front. And we'll have to FOIL the binomial. That's 1 minus 2 cosine 2x, don't be leaving out that middle term, plus cosine squared 2x dx. We have a cosine squared 2x. In order to integrate these even powers, you have to use a half-angle identity. So that's going to be 1/2 times the quantity 1 plus cosine of the double angle. In this case, that's 4x. 1 plus cosine of 4x. Make sure you get that one right. We can distribute the 1/2 and combine like terms. 1 plus 1/2 will be 3/2. That will get rid of this one term. We can integrate what's left over. 1/4 times the quantity, 3/2 x, minus the sine of 2x. You have to divide by a 2. That will cancel the 2 out front. Over here we have to divide by 4. So we'll end up with plus 1/8 sine of 4x plus c. And that, except for distributing the 1/4, is it. We have a procedure. If you're dealing with either sine to the nx or cosine to the nx, what do? If n is even, you use half-angle identities. If n is odd, you use the Pythagorean identity and use substitution. This procedure even works if you have a mixture of sines and cosines. In this case, all of the powers present are even. We'll use half-angle identities. So we'll have 1/2, 1 minus cosine of 2x squared times 1/2, 1 plus cosine of 2x dx. 1/2 squared is 1/4 times 1/2 is 1/8. We'll bring a 1/8 out of the entire integral. If I take a 1 minus cosine x and multiply by a 1 plus cosine x, that gives me a difference of squares. I'll have one more factor of 1 minus cosine 2x left over, but I'll have 1 minus cosine squared 2x from the difference of squares product. Foiling, we'll have 1 minus cosine 2x minus cosine squared 2x and then plus cosine cubed 2x. You can see that on the third term we have to use a half-angle identity again. On the fourth term we'll use a U substitution. We'll take care of these first two terms to begin with. We'll have x minus 1/2 sine of 2x minus 1/2 the integral of 1 plus cosine of 4x dx, and then on the last term we'll have the integral of 1 minus sine squared 2x cosine of 2x dx. Here we'll have minus 1/2 x. We'll have to distribute the minus, and we'll get a 1/4 times 1/2 is 1/8 sine of 4x. And then on the last term, it's u is the thing that has its derivative. du is twice cosine of 2x dx. we'll have this 2 divided off onto the other side. And so that gives us plus 1/2 the integral of 1 minus u squared du, close bracket. We have an x minus 1/2 x. That's a positive 1/2 x. We have minus 1/2 sine of 2x and also minus 1/8 sine of 4x. Then we have plus 1/2 u minus u cubed over 3, close bracket, plus a constant of integration. The only thing left to do is to substitute for u. We have 1/8, 1/2 x minus 1/2 sine of 2x minus 1/8 sine of 4x plus 1/2. U was sine of 2x minus 1/6 sine cubed of 2x, close bracket, plus a constant of integration, modulo some simplification. We're pretty much done. In our next example, we're going to integrate sine cubed x times the cosine of x to the minus 2. The minus will not mean inverse, just reciprocal. Here's what we'll do. We'll split off one sine. The sine x dx is going to become the du. Sine squared is 1 minus cosine squared x. We'll have times the cosine of x to the minus 2, the sine x dx left over. U is going to be cosine of x, so du is minus sine x dx. Minus 1 minus u squared to the power of u to the power of minus 2 du. So we'll have minus u to the minus 2 minus 1 du. Integrating, we add 1 to the exponent and divide by the new exponent, and then minus u plus c. We can distribute this minus. Everybody becomes plus. 1 over cosine is secant plus cosine x plus c. That's it. What happens if you have an odd power of sine and an odd power of cosine? What if they're both odd? In this case, you still use a u substitution. Anytime at least one of those powers is odd, you'll use a u substitution. Let's convert cosine cubed into 1 minus sine squared x with 1 cosine x left over, the cosine x dx. We'll have u equals sine x. Du is cosine x dx. The integral is transformed into u cubed times 1 minus u squared. The cosine x dx goes away to become du. Don't be abusing these differentials. They're important. If you start abusing them, they will abuse you back. We're going to get the integral of u cubed minus u to the 5th du. That's u to the 4th over 4 minus u to the 6th over 6 plus c, or 1/4 sine to the 4th x minus 1/6 sine to the 6x plus a constant of integration. We've seen how to deal with sine mx cosine nx dx. If both m and n are even, then you use half-angle formulas. Otherwise, if at least one of these is odd, you use a U sub. There is an alternative way of dealing with powers of sine or cosine by themselves, called a reduction formula. Let's derive a reduction formula for cosine to the power of nx. Here's how this works. We're going to split off one of the cosines. And then we're going to use integration by parts. For integration by parts, there's a u part and a dv part. In this case, u is the thing that you'd rather differentiate. It's going to be cosine to the n minus 1 x. And dv is going to be everything else, including the differential. Du will be found by calculating a derivative, and here we need to use the chain rule. We'll bring the power down using the power rule for derivatives. Cosine n minus 2x, but then we have to multiply by the derivative of the inside, which is minus sine x dx. V, on the other hand, is just sine x. We'll put this into a box to encapsulate it. We'll have the integral of cosine to the nx dx is uv, that's cosine to n minus 1x sine x, minus the integral, I'll leave a gap because we have some things to bring out of the integral, of v du. We have a negative, so that's going to become a plus. The n minus 1 will move out of the integral. We'll have sine n minus 2x sine squared x dx. We'll convert the sine squared into 1 minus cosine squared and then distribute. We'll have cosine to the n minus 1x sine x plus n minus 1, the integral of cosine to the power n minus 2x dx. And when we distribute, we'll get minus n minus 1, the integral of cosine to the nx dx, because we add the exponents. Isn't this what we started with? We've seen this trick before. You have to sling this one term to the other side and join it with the other side. But if I take this to the other side, the minus becomes a plus. We'll have n minus 1 of the integrals plus 1 of the integrals. It follows that we have n of these integrals equal to cosine to the n minus 1x sine x plus n minus 1 times the integral of cosine to the n minus 2x dx. To solve for the integral, all we have to do is multiply both sides by 1 over n. We'll have 1 over n here and 1 over n here, and this gives us what is called a reduction formula. Say n is equal to 5, then we'll get cosine to the 4th x sine x, and then 4/5 the integral of cosine to the 3rd x. So we reduce the powers pairwise by 2 each time we apply the reduction formula. How then would we integrate cosine cubed? We'll plug in 3 over here. We'll get 1/3 cosine squared x sine x plus 2/3 the integral of cosine to the 1x, and we know how to integrate cosine x. So repeated applications of the reduction formula eventually leads to the answer. Okay, the reduction formulas for powers of sine or cosine aren't particularly useful because we already have better means for calculating those. either half-angle identities or U substitutions. Where this reduction formula really comes into its fore is with powers of tangent or secant. Suppose we have tangent to the nx dx. How are we going to deal with this? We'll begin by splitting off not one tangent, but two. Do you remember a Pythagorean identity involving tangent x? You might remember that. Let's see. We know that cosine squared x plus sine squared x is 1. And if we divide everything in sight by cosine squared x, we'll get 1 plus tangent squared x equals secant squared x. If we move the 1 over, tan squared x is secant squared x minus 1. Let's see where this leads. We have tangent of to the power of n minus 2x. Over here we're going to have secant squared x minus 1. So we'll have secant squared x dx minus the integral of tangent to the n minus 2x dx. You can see a reduction formula seems to be coming along. We just have to figure out what to do with this first integral. For that, you can see that you might be able to do a U substitution. U is tangent x. Do you remember the derivative of tangent? Secant squared x. I feel a U sub coming on. Integral of u to n minus 2 du. And then this integral we're going to leave alone because that's going to be for our reduction formula. So we'll get 1 over n minus 1 u to the n minus 1 minus the integral of tangent to the n minus 2x dx. We're almost done. We just need to substitute back. We'll have 1 over n minus 1 tangent to the n minus 1x is the integral of tangent to the n minus 2x dx. This works, of course, provided n is not 1. If n is equal to 1, it's a u sub straight up. You'll convert tangent to sine over cosine and set u equal to cosine x. You'll end up with a minus because the derivative of cosine is minus sine. So you'll have to put a minus in. You get minus the log of the absolute value of cosine x, which is the log of the secant of x plus c. So in the case n equals 1, there's a simple procedure for handling that one excluded case. Let's calculate a reduction formula in the case of secant to the nx dx. In this case, what is the derivative of secant? Isn't it secant tangent? How are we going to deal with that? What we'll do is we'll split off two of these. And we know how to integrate secant squared. And we know how to differentiate secant to the n minus 2x. It looks like integration by parts. U is secant to the n minus 2x. dv is secant squared x dx. Using the chain rule, we'll bring the power down, subtract 1 from the exponent, but then we need to multiply by the derivative of the inside. V is, of course, tangent x. We have uv minus v du minus, I'll leave a gap, we'll have this n minus 2 coming out. We have a secant to the n minus 3 times secant. That's secant to the n minus 2x. We have a tangent times a tangent. That's tangent squared x. Looks like we need to use a Pythagorean identity to convert tangent squared x to secant squared x minus 1. Do you remember that identity? We have then secant to the n minus 2x tangent x. We'll have minus n minus 2 integral of secant to the nx dx, and then minus is plus n minus 2 integral of secant to the n minus 2x dx, distributing to the minus 1. You can see this has a secant to the n just like on the other side. So this term needs to be sent to the other side. We've danced this dance before. We know how this is done. N minus 2 of them plus 1 of them gives us n minus 1 of them. We'll have secant to n minus 2x tan x, and then plus n minus 2 times the integral of secant to the n minus 2x dx, subtracting 2, reducing the power by 2 each time we apply the formula. The only thing left to do is divide by n minus 1. And that gives us the reduction formula. So for example, if we're integrating secant cubed x dx, we'll get 1/2 secant x tangent x minus 1/2 the integral of secant x dx. Now, do you remember the integral of secant x dx? We'll derive that, but first I'll just write down what the answer is. So we'll get 1/2 secant x tangent x minus 1/2 the log of the absolute value, secant x plus tangent x plus c. I'll show you how to derive this again. Remember, the integral of secant x is one of those garbage can calculations. The trick is to rewrite this with a secant x plus tangent x over secant x plus tangent x, multiplying by 1. We're not changing the value of the integrand, only its form. And then we'll distribute, but we'll reverse the order of the product to get secant x tangent x plus secant x squared x, still over secant x plus tangent x dx. At this time, you can see that the secant has a derivative of secant tangent, and tangent has a derivative of secant squared. That means the integrand is of the form f prime over f. We immediately deduce that the integral is the natural log of the absolute value of secant x plus tangent x plus c. And for sake of completeness, let's look at the integral of tangent x, which I already described, splitting this into sine over cosine. Here, we set u equal to cosine x, so that du is minus sine x dx. We have the sine x dx, but not the minus. So the integral is transformed to minus the integral of 1 over u du, or minus log absolute value plus c. That's minus log the absolute value of cosine x plus c. If you bring the minus up, it's the log of the absolute value of the secant of x plus c. Now let's see what happens if we have something like tangent cubed x secant squared x dx. The derivative of tangent is secant squared, which is fortunate. We have an even power here. We'll set u equal to tangent x. du is secant squared x dx. So the integral is transformed into the integral of u cubed dx. That's u to the fourth over 4 plus c, or 1/4 tangent to the fourth x plus c. This simple substitution worked out only because we had an even power here. To see that the method still works, even if we write secant to the fourth x, remember 1 plus tangent squared x is secant squared x. So we'll take two of these and write that as a 1 plus tangent squared x, and we'll leave the secant squared x out here all on its own. We're now ready to do the u substitution. U equals tan x du is secant squared x dx. So the integral is transformed into the integral cubed 1 plus u squared du. The integrand is u cubed plus u to the fifth. So when we integrate, we'll have u to the fourth over 4 plus u to the sixth over 6 plus c, or 1/4 tangent to the fourth x plus 1/6 tangent to the sixth x plus c. It worked because the power on secant was even. So what happens if the power on secant is odd? If we're integrating tangent cubed x secant cubed x, here's what you do. Split off one tangent and one secant. You know that the derivative of secant is secant tangent. We can convert the remaining tangents to secants using the Pythagorean identity. That's going to be secant squared minus 1 secant squared x times secant x tangent x dx. It's at this point we simply say u equals secant x, so that du is secant x tangent x dx. We'll have then squared minus 1 u squared du. And the rest is easy. We'll have u to the fourth minus u squared, so we get u to the fifth over 5 minus u cubed over 3 plus a constant of integration. That's 1/5 secant to the fifth x minus 1/3 secant cubed x plus c. It still reduces to a substitution, but it's the other way around. You convert everything else to secants. Note, however, that we'll have trouble. Note, however, that we'll have trouble with this method if the power on tangent is even. It was important that we be able to split off one tangent and have an even number left over in order to use the Pythagorean identity. If the power on secant is odd and the power on tangent is even, then a different procedure is indicated. You convert the tangents at that point using the Pythagorean identity all to secants, and then use the reduction formula for secant that we derived earlier. I'll show you an example. If we're integrating, say, tangent squared x secant cubed x dx, now we'll convert the tangent squared into secant squared x minus 1, still times the integral of secant cubed x dx. Distributing, we'll break this into the integral of secant to the fifth x minus the integral of the secant cubed x. And at this point, we use reduction formulas. I'll leave it at that. So by way of review, have three cases to deal with. If n is even, then what you do is you split off two of these, convert the others to tangent, and then do a u sub. If m is odd, you split off a tangent and a secant, and then you do a u sub. U equals secant x. And third, if m is even and n is odd, then you convert all the secants and use reduction formulas. There are similar formulas for dealing with cosecant and cotangent, but their occurrence is rare, so I'm going to leave those for you to look up when the time comes. We're next going to move on to trig substitutions. These are only used in the following cases. You have a constant squared minus a variable squared under a radical, a difference of squares under a radical. The difference could go the other way, in which case you'll use a different trig substitution, or you might have a sum of squares under a radical. The strategy is pretty much the same in each case. The idea is to take either a sum or difference of squares, convert it using a Pythagorean identity to a single perfect square, which allows you to get rid of the square root. Here's how this works. In the first case, x is going to be a sine theta. You'll have a squared minus a squared sine theta. Plugging this in, you'll have the square root of a squared minus a squared sine squared theta. The a squared can be factored out of the square root. Normally we put an absolute value. Let's ignore that for now. Square root of a times the square root of 1 minus sine squared theta. That's cosine squared theta. And let's forget the absolute value here as well for now. Sometimes you do have to worry about this absolute value. But a times the cosine of theta. That allows you to get rid of the square root. That's a big advantage. In this case, it's a slightly different substitution. You have to use secant theta, and that's because you'll get a squared secant squared theta minus a squared. Of course, the a comes out. Secant squared minus 1 is tangent squared. So you get a times the absolute value of tangent theta. In the last case, x is going to be a tangent theta, because in this case you get a squared plus a squared tangent squared theta. The a comes out. You get the square root of 1 plus tangent squared is secant squared theta. And so you get a times the absolute value of secant theta. So in each case, we can get rid of the square root by making an appropriate trig substitution. That trig substitution requires the use of one of the Pythagorean identities, either 1 minus sine squared theta is cosine squared theta, or secant squared theta minus 1 tan squared theta, or 1 plus tan squared theta is secant squared theta. These are the identities we're going to use, these Pythagorean identities, in order to get rid of the square roots. Now let's see how this works out in practice. Let's look at the integral of dx over 9 minus x squared to the power of 3/2. We have a radical because of the 2 in the denominator here. Because of the form, here's the way you deal with this. You take the square root of the constant term and multiply by sine theta in this case. Because we're going to use the identity 1 minus sine squared is cosine squared. Yes, we have to account for the dx. Dx is 3 cosine theta d theta. We're going to have 3 cosine theta d theta over 9 minus x squared is now 9 sine squared theta, and that's to the power of 3/2. Oops, I forgot my square. We'll have the integral of 3 cosine theta d theta. In the denominator, we'll factor the 9 out. 9 times the quantity 1 minus sine squared. But the 9 still gets raised to the power of 3/2. Do the square root first. The square root of 9 is 3. Raised to the 3 power is 27. What's left over is 1 minus sine squared. 1 minus sine squared is cosine squared. Cosine squared to the 3/2 is going to end up being cosine cubed. I'll write this as 1/9, the integral cosine theta over cosine cubed theta d theta. We'll have 1/9 the integral of secant squared theta d theta, and that's 1/9 tan theta plus c. You might think we're done, but we're not. We have to deal with x's. The original problem was framed in terms of x. We need to get rid of these thetas. I'll show you how to do that. The trick involves using a right triangle. We have sine theta is x over 3, and sine is opposite over hypotenuse. If this is theta, we'll have x over 3. The adjacent side can be calculated using the Pythagorean Theorem. It's going to be 9 minus x squared under a radical. This had better show its head again, or else you screwed up. We're interested in tangent theta, but tangent is opposite over adjacent. So we have 1/9 times x over the square root of 9 minus x squared under a radical plus c, and that is the answer. Let's do an example where you already know the answer. In this case, you'll recall that y equals the square root of r squared minus x squared. If you square both sides, gives you y squared equals r squared minus x squared, and shipping this term to the left, you have x squared plus y squared equals r squared. You know that that's the formula for a circle, but since we're using the principal square root, which is the non-negative one, we're only getting the top half. So we know the answer should be 1/2 pi r squared. 1/2 pi r squared is the value for this integral. But let's see if we can calculate the integral using trigonometric substitutions instead of geometry. The substitution here is x equals the square root of the constant r times sine theta, which means dx is r cosine theta d theta dx. Now, if x is equal to r, we can cancel the r's and get sine theta equals 1. Sine equals 1 at pi over 2. Completes the cycle at 2 pi, half the way at pi. Pi over 2 is where you get to 1. And what about if x is negative r? Where is sine equal to minus 1? Well, in this case, you need to go backwards to minus pi over 2. We'll have the square root of r squared minus r squared sine squared. I'll write an s instead of the entire sine theta. Dx is r cosine theta d theta. We can get this r squared coming out of the square root as an r, the radius is positive, times an r gives us r squared, the integral from minus pi over 2 to pi over 2. Minus sine squared is cosine squared. Square root of that is cosine squared. We're integrating cosine squared theta d theta. To integrate cosine squared theta requires the use of a half angle identity. So that's r squared over 2, the integral from minus pi over 2 to pi over 2 of 1 plus cosine of 2 theta d theta. The period of cosine 2 theta is pi, which happens to be the length of the interval that we are integrating on. Since you're integrating over an entire period, cosine 2 theta will give you nothing in the answer. The interval is length pi, and we're integrating 1. That gives us pi. So the answer is 1/2 pi r squared, just like before. In our next example, we're going to find the arc length of the curve y equals x squared on the interval from 0 to 2. You'll remember these arc length problems almost always go straight to hell. You'll see that here. Remember the formula was the integral from a to b, the square root of 1 plus f prime of x squared dx gives you the arc length. So for us, s is going to be the integral from 0 to 2 of the square root of 1 plus the derivative of our function squared dx. And you can see you have a classic trig sub. Here's how you do this. Take the variable term and take its square root. Now take 1, its square root is 1, and it's 1 plus variable stuff squared, so that's going to be a tangent. We'll get 2 dx equals secant squared theta d theta. We have the dx but not the 2, so I'll put the 2 over here. I'm not going to switch the limits of integration. If x is equal to 2, tangent theta equals 4. I don't know anything for that, so I'm going to do this as dot to dot. I'm not going to use 0 and 2 because that would be untrue. I'll have theta variables here, so I need theta limits, but I'm too lazy to calculate those theta limits, so I'm just going to write the integral from dot to dot. I'll have the square root of 1 plus 4x squared is tangent squared theta. And now we have this 1/2 secant squared theta d theta. 1 plus tangent squared is secant squared. Square root of that is secant. We'll be integrating secant cubed. An odd power on secant. What do we do? Using our reduction formula, we'll get 1/2 secant theta tangent theta plus 1/2 log absolute value secant theta plus tangent theta, and then we're evaluating from dot to dot. No, I didn't remember the reduction formula. I had to look it up. We can take these 1/2s out, but to convert back to x requires a triangle. Tan theta is opposite over adjacent. Using the Pythagorean theorem, the hypotenuse is the square root of the quantity 1 plus 4x squared. Now, we'll have 1/4 Tangent is 2x. Secant is hypotenuse over adjacent, so that's the square root of 1 plus 4x squared, plus the log of your secant, square root of 1 plus 4x squared, square root into here, plus 2x, close bracket, evaluated now from 0 to 2. Now it's appropriate to use 0 and 2 again because we're back in terms of x. Now, plugging in the 2, we'll have 4. 2 squared is 4 times 4 is 16 plus 1 is the square root of 17. Plus the natural log of the square root of 17 plus the 2x, which is 4. Minus what we get when we plug in 0. We'll get 0 in the first term. On the second term, we get the log of the absolute value of 1, which is 0 in this case. We can simplify only a little bit by distributing, but our answer is essentially this constant. Remember what that represents. That's the length of the curve. In our next example, we'll integrate from 1 to 4, the square root of x squared plus 4x minus 5 all over x plus 2 dx. To get this to work right, you first have to complete the square under the radical. X squared plus 4. X. To complete the square, you divide the coefficient of x by 2 and square it. You want plus 4. You have minus 5, so you have to subtract 9 so that you'll get a net of minus 5. We'll now have the integral from 1 to 4, the square root of x plus 2 quantity squared minus 9, all over x plus 2. Because it's variable stuff squared minus a constant, we're going to use a secant for our substitution this time, because secant squared theta minus 1 is tangent squared theta. That will allow us to get rid of the square root. The substitution is the square root of the variable stuff. That's going to be x plus 2. No absolute values on this. Equals the square root of the constant times the trig substitution, which in this form must be secant theta. Dx is then 3 secant theta tangent theta d theta. So this gives you our substitution information. Looks like transforming the limits of integration won't help. So I'm going to integrate from dot to dot. I'll have the square root of x plus 2 squared is 9. Secant squared theta, still minus 9, all over 3 secant theta, but our dx gets transformed into 3 dx, 3 secant theta tangent theta d theta. Now we simplify. We can cancel these 3's and the secant theta. The 9 comes out of the square root as a 3, leaving a 1 in this position. Secant squared theta minus 1 is tangent squared. Square root is tangent. We will be integrating tangent squared theta d theta. To integrate tangent squared, we'll use the Pythagorean identity to convert that into secant squared theta minus 1. The integral of secant squared is tangent. And the integral of 1 is just theta. Still evaluating from dot to dot. We, at this point, need to remember our triangle. Secant theta is hypotenuse over adjacent. That's going to be x plus 2 over 3. The remaining side then, by the Pythagorean theorem, is x plus 2 quantity squared minus 9 under a radical. That had better show its ugly face again, or else you screwed up. We now make the appropriate substitutions. Tangent theta is opposite over adjacent. Now how about that theta? There are different ways of doing this. I don't really want to use an arc secant. Arc cosine might be easier to deal with. Cosine theta is the reciprocal of secant. If secant is x plus 2 over 3, cosine theta will be 3 over x plus 2. I'll use arc cosine then of 3 over x plus 2. We're evaluating, remember, from 1 to 4. Plugging in 4, let's see, I guess we can distribute this 3. That'll give us a 3 in this spot. Plugging in 4, 4 plus 2 is 6, squared is 36, minus 9 is 27. The square root of 27 is 3 root 3. Plugging in 4, 3 divided by 6 is 1/2. The arc cosine of 1/2 is pi over 3. Now we need to plug in x equals 1. 1 plus 2 is 3, squared is 9, 9 minus 9 is 0. 3 divided by 3 is 1. Inverse cosine of 1 is 0. Looks like our answer is 3 root 3 minus pi. I want to do one more problem. Let's suppose that we have an ellipse. And it's been translated. Normally, ellipses look like x squared over a squared plus y squared over b squared equals 1. But I'm going to translate this c units over so that the origin is at one of the foci. X minus c squared over a squared plus y squared over b squared equals 1. For ellipses, a is the length of the semi-major axis and b is the length of the semi-minor axis. There is a relationship between those two and the distance to the focus. C squared is a squared minus b squared for ellipses. So here's the deal. Johannes Kepler noticed, published I believe in 1609, that planets sweep out equal areas in equal times and their orbits around the sun are elliptical. That was a huge revolution at the time because before that people figured, well, okay, maybe the Earth is at the center of the universe, or maybe the sun after Copernicus. But the Copernicus revolution really didn't take off. His ways of calculating the positions of the planets using exact circular orbits were not as accurate as the use of epicycles before that. Epicycles assume that planets move on circles, crystal spheres rolling on crystal spheres. That actually had better accuracy than Copernicus's method of calculating the positions of the positions of the planets in their various orbits. Though Kepler had another idea based on numerous computations and observations of the planet Mars. He discovered that planets don't move in circular orbits, but rather in elliptical orbits, with the sun at one of the foci. And they sweep out equal areas in equal times. How did Kepler figure out the areas of these elliptical sectors from one of the foci. What he did is he approximated and used little circular sectors. We can one-up Kepler by calculating the exact area of one of these sectors. First, solving for y, you get plus or minus b square root of 1 minus x minus c squared over a squared. Here's our elliptical sector. Let's suppose this goes from x1 to x2, and we want to calculate the area of that sector. If we simply integrate from x1 to x2, it won't give us exactly what we're looking for. It doesn't give us this of a triangle, and it gives us this weird trapezoid, which is too much. Here's what we'll do. We'll take this area of this triangle, 1/2 base times height, but now we have too much. What we need to do is subtract out this other triangle, and that will give us the area of the sector, minus 1/2 base times height. The trick now is to calculate this integral. So let's focus just on this integral and not worry about the limits of integration. The problem is to find an antiderivative. After we have an antiderivative, we can apply the fundamental theorem of calculus to evaluate this definite integral. No problem. Let's just focus on the integral by itself for now. The integral was b times the square root of 1 minus the quantity, x minus c squared over a squared, all times dx. This is a difference of squares under a radical. That's a clear indication that we're dealing with a trig sub. It's of the form constant minus variable stuff squared. So this is a sine theta problem. You take the square root of the variable term, don't worry about absolute values on this, equals the square root of the constant, which is 1, times the function, which in this case is sine theta. We'll have 1 over a dx equals cosine theta d theta. We'll have 1 minus sine squared theta. This a doesn't appear here, so we'll have to move it over. Dx will be replaced by a cosine theta d theta. So the a comes out, and we get ab, the integral of 1 minus sine squared is cosine squared, square root is cosine, times cosine is cosine squared theta. An even power of cosine means half angle identities. We'll have AB over 2 times theta plus 1/2 the sine of 2 theta plus c, 1/2 because of the 2 in front of the theta. Now we use the double angle identity for sine. You'll recall that the sine of 2 theta is 2 sine theta cosine theta. So we'll have AB over 2 times theta plus 1/2 times 2 times sine theta cosine theta plus c. Now we need to use a triangle. You might remember our definition was sine theta is x minus c over a. Sine is opposite over hypotenuse. The remaining side is going to be the square root of 1 minus x minus c squared over a squared under a radical. Sine theta was x minus c over a. Theta will be the arc sine of x minus c over a. Sine theta, x minus c over a. Cosine theta is adjacent over hypotenuse. That's the square root of 1 minus x minus c squared over a squared plus c. We'll use this for our antiderivative and then evaluate at the endpoints and subtract, and then we can find the area of the sector. Since satellites around the Earth have the same orbital characteristics, they orbit in the shape of an ellipse, they have the Earth at one focus, they sweep out equal areas in equal times. That means to track satellite positions will require the use of this formula. Satellite tracking requires calculus 2.